Hello everyone. Today we are going to present our work, VMINer, Versatile Multiview Inverse Rendering with Near and Far Field Light Sources, from Peking University, HKUST, and Light Illusions. Given multiview images of an object, VMINer leverages all present lighting conditions during the capture, such as far field lights or flashlights, to enhance the quality without losing practicability. It reconstructs the scene geometry and material disentangled with lighting as 3D implicit fields. After training, the 3D fields are extracted to triangle meshes with UV textures for seamless integration into industrial renderers. These meshes can be used in various applications, such as inserting them into a new environment with unseen lighting. Now let's talk about our motivation. Taking images under consistent lighting as inputs, common 3D reconstruction methods, such as NeRF or 3D Gaussians, represent only the radiance field, which is a complex product of the external lighting interacting with the intrinsic geometry and material of the scene. But if we want to put the reconstructed object into an unseen environment, the entangled nature of the radiance prevents these methods from realistically rendering the object, as the original lighting is embedded within the newly rendered scene. In contrast, inverse rendering approaches achieve reliable reconstructions by separating the intrinsic properties from external lighting. Then the reconstructed material and geometry can be combined with any unseen lighting to relight the object. However, a fundamental challenge in inverse rendering is the severe inherent ambiguity. For example, without prior information about how a plate would look like, from images under one fixed lighting, one cannot judge whether the dark region is due to the geometry, the material, or the lighting. But if we observe the object under another lighting, we can find that the dark region is not due to the material. Otherwise, it would sustain under the new lighting, which drives us closer to the correct answer. From this example, we know that observing under varied lighting helps to alleviate the ambiguity. Some existing methods, such as NERD and TensorIR, leverage inputs under multiple but only far field lighting to keep unknown lighting parameters manageable. The far field assumption causes an increased workload on the data collection and pose estimation process, as throughout the capture, the environmental lighting setup has to be changed. Another method, wildlight, uses a camera-collocated flashlight in addition to the ambient lighting. It does not harness available observations under the ambient lighting for inverse rendering, leading to a degradation of its estimated material. To address the aforementioned shortcomings summarized in this table, we introduce VMINer. Its distinctive feature is that it uses a lightweight yet inclusive lighting model for different far and near-field light sources, and efficiently leverages all available observations under each lighting for disentanglement, making the most out of whatever light sources are at hand to boost the practicality and quality of the reconstruction. VMINer takes multiview RGB images under possibly varied lighting as input. Each image is illuminated by one far field lighting whose index is given by far index, and near field lights whose on-off states are given by near on-off. Each far field lighting is modeled as spherical Gaussians with unknown lobe axis psi, amplitude mu, and sharpness lambda. Each near-field lighting is modeled as a point light with movable position p and anisotropic radiation as spherical harmonics coefficients h. Incoming radiance L can be queried at any position x and direction omega. Scene geometry, material, and radiance are represented as 3D implicit fields. The geometry MLP processes the hash grid-encoded position x to get the SDF-S, the appearance descriptor z, and the surface normal n. The material MLP uses another hash grid and processes the geometric information to predict SVPR24 parameters beta. The radiance MLPs additionally take SH-encoded view direction v and lighting embeddings f to get the neural radiance c under each lighting condition. Although VMINer does not strictly require a radiance field, incorporating it eases the geometry optimization. Also, it can serve as supervision to better separate appearance under each lighting, and can be used as indirect lighting. VMINer adopts NUs to transform the SDF values into discrete opacity values for volume rendering. The neural radiance of a pixel, capital C, is predicted separately under each lighting, then added up to CRF according to the per-image lighting condition. This value is compared to the observation CGT for training. The physically based surface rendering models the observed radiance as reflected from a single surface point. VMINer uses secondary ray tracing to compute the direct lighting visibility and indirect lighting. To compute the radiance under direct far field lighting and indirect lighting, Monte Carlo integration is employed to evaluate the rendering equation and get the reflected radiance. For the radiance under direct near-field lighting, as for each surface point the light originates from a single direction, the integral simplifies to a multiplication and can be evaluated efficiently. The PBR radiance is also summed up and compared to the observation. Also, for each separate lighting, we use the neural radiance as an additional supervision signal. Now we show the comparison of VMINer with other state-of-the-art methods. We first show qualitative comparison on 3 synthetic scenes. The first scene is barrel sofa. The second scene is Lego. The third scene is Trooper. We show qualitative comparison on 2 real-world scenes. The first scene is Guan Yu. The second scene is Debu Gundam. Here are the quantitative comparison results. The table shows that VMINer achieves higher quality results in a much shorter time, about 45 minutes on a single RTX 3090 GPU. In conclusion, we find that varied lighting helps alleviate ambiguity in inverse rendering tasks, and near-field lights such as flashlights are handy and effective light sources. Thanks for watching.